everyone. So yeah, good morning. My name is Michael Ramos from Siemens, Canada. I'm a senior power system consultant there. And yeah, it's a big pleasure for me to be here with you, sharing our experience with power systems simulation. And of course, a great opportunity to learn more and more with you. So today, yeah, I will discuss a little bit and present some results and some simulations about a project where we perform acceptance tests of a wind farm power plant using EMTP tool. So yeah, I'm very glad that I heard that in the future version there will be some functionalities that we can automatize this process. Yeah. So yeah, this is just the agenda that I will try to cover. Some motivations why we'll discuss about these simulations using generic models. The main components that were modeled in EMTP, the power flow representation and dynamic representation. This is just to give an idea the difference, because in this project particularly, we modeled the system using both programs, EMTP and PSSC, and not because we wanted to compare the results, but because this was a requirement from our client. So the client wanted both models working and responding well and as close as possible in EMTP, in PSK and PSSC, right? So because of this, I will give you an idea the difference in terms of power flow and dynamic. Setting the parameters and the acceptance tests that we perform and the results, so we can see that both models responded very well, and yeah, some conclusions. So in terms of motivations, yeah, the main reason that why we decided to use generic models in this case is because this is not a new power plant. So this, let's say, an old wind farm, and this client or this power plant doesn't have user-defined models available. So because of this, we decided with our client and with the manufacturer develop the model using the WECC generic model, right? And in fact, this is something not bad, because someone could ask me, oh, but why you are using generic model? Because we know that when we use user-defined models, we can get a more accurate result. We can represent better our dynamic behavior. But on the other hand, we know that some utilities, many ISOs still request both models. So today, many ISOs, utilities, if you are integrating a new renewable power plant, you need to provide the UDM and also the generic model, right? And the reason why they request this generic model is because depending the kind of study that you are simulating, generic model can give you a faster response if you are simulating a large or extended book power system, right? So this is still very useful, this generic model. So because of this, we are using this generic model here. And yeah, here I just highlight some reasons that why generic model is still crucial. And just to highlight these two reasons, so the standardization and comparability. So we can compare the results and benchmarking across different studies, projects, and technologies. So this is something important when you are simulating generic models. So just some ideas, right, in terms of why this kind of model is very useful today. Yeah, just to give you an idea about this power plant. So the system that we develop at this project contains 121 wind turbines, a total rate megawatt to 102.85 megawatt. And this capability, this reactive power capability, Qmax and Qmin around 34 megavar, right? So for this plant, we have six feeders, and we have this equivalent generator here representing 21 wind turbines, 21 pad mounted transformers, and so on. So in terms of load flow representation, in this case, as I will show you, we represent this system slightly different in PSSC and in EMTP, but could be the same, just because the client requested this format. So in PSSC, we developed the 6 feeders, and in EMTP, we develop as a single machine, right? And this is not bad if you check some standards, some documents from WECC, or even some papers, books, you see that when you are representing your renewable power plant for transmission planning studies, you can represent your power plant as a single machine, right? But what I want to highlight here is that we'll see that even with this different, not different models, but different way to represent the same system, we'll see that we are able to get the same results. Yeah, here's just to highlight, right? So the brains inside of the wind farm were represented using this technique, available in many papers, in some documents from WECC. So we use this technique to represent the collector system equivalent, and we just use this approach to represent the wind turbine generator equivalent and the pad mounted transformer equivalent. Pretty simple, right? Just following that approach. So from the components perspective, how these components were represented. So as I mentioned here, you can see the way that the system was modeled in PSSC for the load flow analysis. So as I mentioned, we represent all feeders, and in EMTP, we represent using the WECC model available in the standard library. And if you go inside of the component, we just use the component that are available there. And as I mentioned, we could change this model inside to represent at the same way, right? Of course, that we should do some adjustment here, some adjustments here to represent the same way with different feeders. But again, this wasn't the case. The client wanted the model in PSSC with all feeders in an equivalent model in EMTP, right? But just to give you an idea, the differences. So yeah, one test that this is not an acceptance test, but something to make sure that the model is working well. So here, as you can see, when you solve the load flow in PSSC, it's a simple load flow model. So you'll see something like that. Here is the POI, and the flow at the POI is around 100 megawatt, more specifically 99.98 megawatt and minus 8.42 megavar. And here in EMTP, when we solve the load flow before initialize the simulation, this is the result that we got at the POI, 99.89 minus 7.46 megavar, right? On the other hand, if this model is correctly adjusted or set, once you initialize your simulation, and here, as you can see at these plots, we can get exactly the same flow here at the POI in EMTP. As Professor Jean mentioned, very fast, right? So we can make sure that at the steady state, the models are exactly the same, right?
If you don't mind, use the laser don't see you on the screen. You have to stay in front of the camera.
Oh, for sure.
Pointer is on top.
Where is the here?
Yeah.
Oh, yeah, for sure.
This way they can see you.
Yeah,
and
yeah,
they
yeah.
can see you on the screen.
Oh, yeah.
Please.
Not the laser, but they will see you on the screen.
Okay. Where is the camera?
The camera is the computer.
Oh, okay. Sounds good. Okay. Yeah. Sorry, guys. So yeah. So here, as you can see, we can. This is the EMTP plot, active power, reactive power at the POI, right? With no disturbance applied at the system, you can clear see that we got the same flow at the POI. In terms of dynamic representation, so as I mentioned, you can find these statements here in some documents, right? But as I mentioned, these generic models are simplified positive sequence models designed for transmission planning studies, and is very powerful, especially for this kind of simulations involving extensive networks and numerous generators. So this again is one of the reasons that some utilities and ISOs still require this model. And the generic models that we use, so just to give an idea, the models in EMTP and the equivalent models in PSSC. Yeah, here I just highlight. I just highlighted here the PPC model, right, used in EMTP and PSSC, just to show you a difference. As I mentioned here, for example, because in PSSC we represented all feeders in the power plant, the Q reference and P reference signals before. These signals won't send directly to the turbines. These signals go directly here to this auxiliary component, right? And these auxiliary components will, let's say, split the signal or divide the signal and send the equivalent signal for each equivalent generator, right? Here in EMTP, because we are just using a single machine representation, these signals go directly here to this equivalent inverter model. But again, if you could do something similar here in EMTP, and this is something that, in my opinion, is a very powerful feature in EMTP. You can, create and adapt your model. Of course, that you need to have the knowledge to do this, but it's very flexible, right? You can create your component, and this is something that is not easy to do. For example, in PSSC, you can combine some components, but the components must be available in the standard library. If the component is not there, you need to develop the component from the scratch using Fortran. So, but this is something possible, and to be developed in EMTP. Just here is just to give an idea in terms of interface, right? And just to highlight the differences. So here in terms of interface in EMTP, when you start modeling, let's say, a new power plant or modeling your system, you are at the same time setting here the parameters that will be used, during the initialization for the load flow, and even for the dynamic analysis, right? You set all parameters through these windows, for example. But here in PSSC is different. You set only the load flow, and later you need to set the parameters for the dynamics. So you need to do this in different parts, right? This is not connected. And again, I'm not saying here that one is better than another, right? Because I wouldn't say this, right? I think that we have different purpose for these tools. But I just want to give you an idea how this is different, right? And how you can model your system if you need to model, in EMTP and compare with another software. So in terms of acceptance test is performed. So basically, this test is one performed plus high voltage right through and low voltage right through. I didn't, I won't discuss about high voltage right through and low voltage right through because we don't have time, but you could, you know, follow the same approach if you want to simulate these tests. But basically, to run this, to perform these tests as active power control test, reactive power control test, voltage power factor control test, and this droop test in terms of low and high frequency and the primary frequency control. The approach that we developed was through these blocks here, right? So we create these blocks, and here we can control the deviation, right, in terms of power reference, Q reference, voltage reference, power factor reference, and frequency reference that we are setting here at the PPC. So as you can see, these signals go through these pins, and these pins go directly to the PPC. So yeah, once you play with these switches here, these tables that will change the reference at the PPC, you can run these tests using this approach, right? So yeah, the first test and basic test, but I would say one of the most important tests, you know, to make sure that your models are being initialized correctly, is this no disturbance test. So here we have the red line is the PPC, the EMT, sorry, the red line is the PSSC model, and the black dashed line is the EMTP model, right? So as you can see, in terms of active power, reactive power, and voltage, both models are responding very well in terms of initialization, steady state. Here, in terms of reactive power, in EMTP, the signal reached the steady state here after 0.1, 0.2 seconds, but very fast because in terms of the way that the power flow is solved and we initialize, we are connecting, right, the power plant to the grid. So this is something acceptable, right? And yeah, here just to give you an idea, when you are initializing this test, you need to set here if you want to, you know, make sure that you are initializing your system at the same operation point that you are initializing the other model. So you can set here the reactive power reference and active power reference, and set, of course, the Q control mode. So in terms of active power control test, as I mentioned, you can play with these components here to apply a step and change the reference, right? In this case, if you want to change the reference for the active power, you play with this component, right? And as you can see here, we change the P reference directly at the PPC. And here we can see that this purple line is the P reference that we are setting at the PPC. And you can, as you can see, in terms of response, both models in these different programs responded exactly the same, right? Of course, that if you look close, you know, but yeah, we can conclude and see that these models are working very well and at the same way. The same thing here in terms of reactive power, right? When we reduce here the reference, the reactive power in both models responded well, and even voltage. The same for reactive power, and here just to highlight, you know, just another thing that I want to highlight here, to run these tests, of course, that you need to play with this control mode. So if you want to perform this test, you need to make sure that the frequency control here is enabled, right, in this PPC model. And of course, that you need to do the same thing in the other component, in the other model. In this case, you need to set these control modes in EMTP, and of course, in this case, in PSSC. For the reactive power, the same thing. You can play with the reference in terms of reactive power. And yeah, you can see that both models can respond very fast according to the settings in the control, in the components, in the controllers, right? And even the voltage measured at the POI responded very similar. Voltage control, the same thing, but yeah, some points that we check if both models are responding well. We check the speed of this response, and also if both models are saturating here correctly. And as you can see, both models saturated here at the same point and respect the Q max here and the Q min here, right? And even in terms of voltage, both models responded very well. We can see here a slightly difference when we reduce the reactive power reference in terms of speed here. One model responded a little bit faster than other, but to make sure that, oh, why this happened, yeah, some investigation, further investigations must be done, more simulations must be done. But in terms of acceptance tests, yeah, this is acceptable. We don't need to do this in this case. But if you want to understand exactly the difference, we should run more simulations and check the models. But this analysis wasn't developed, right, in this case, because the client was satisfied with this result. In terms of a power factor control test, the same thing. You need to make sure that the Q control mode is set correctly. But again, we test the power factor reference in terms of lagging power factor, leading power factor. And again, you can see that here we are presenting the active power, reactive power, voltage here at the POI, and the power factor measured at the POI. And yeah, you can see that this is a great result. In terms of droop test, I think that this is something interesting to think. Here is the droop test for high frequency. So basically here, we have the active power here at the POI, the reactive power at the POI, the voltage at the POI, and here we have different plots. This plot is the frequency measured in PSSC, and this is the frequency measured in EMTP, right? And what I want to highlight here is the way that this test was performed in PSSC and EMTP. This test was performed in PSSC using a component to play back the frequency and voltage at the POI, right? So we just use a component and increase the frequency at the POI. As you can see, this purple line is the frequency at the POI. And here we have a red line that is the frequency reference set at the PPC, right? And obviously, as you can see, if you increase the frequency, right, at the POI, it means that we are in an over frequency condition. Consequently, we need to reduce our active power, right, at the POI, or our generators must respond in terms of droop control, right? And if you look here, in fact, the active power reduced. But here in EMTP, instead of use this kind of approach, use, let's say, a control voltage that we can increase the frequency, a dependent source that we can change the voltage or frequency at the POI. we apply a step directly at the reference. So the behavior is the same, but we kept the frequency at the POI at 60 Hertz, and we just reduced the frequency reference at the POI in 1 Hertz. So from the control perspective, we still have an over frequency condition, right? Because we just reduced the reference. And we got exactly the same result. Of course, that you could develop a component, you could use a dependent voltage source, frequency source, and change the frequency or voltage at the POI, but you can perform this test using this approach. In my opinion, it's easier and faster than you use a component. You just change the reference, and as you can see, you can get exactly the same response in terms of active power and reactive power. For the low frequency response, the same approach, right? But now is if you look here, the frequency in PSSC and frequency here used to perform this test, the signals are in the opposite direction. So here we reduce the frequency at the POI. So from the system perspective, this is an under frequency condition. So we need to increase the active power injection. And here we increase the reference, right? So we still have a delta F of 1 Hertz. And finally, this test, primary frequency control. Again, we use the same approach, right? Here in PSSC, we just play the frequency directly using that playback component. And again, if you look the shape here of the frequency at the POI, we have the same shape here, but in a different direction, right? Here is the frequency reference at the PPC, okay? And as you can see, the active power responds exactly at the same way in both models, PSSC and EMTP, right? So this is here, this is the, let's say, the easiest way to run this kind of test using PSSC. And yeah, in our opinion, if you play directly here, this is the easiest way to play the frequency and run this kind of simulation. Yeah, just to, in terms of conclusions, just to highlight that in this case, both models responded very well. And even if you have, in this case, one model, let's say with more generators, more feeders, right? And using a single machine model, and even playing some tests in a different way, from the dynamic perspective, you can get the same results, right? Of course, that you need to understand exactly how the PPC works, how the system will respond when you change the frequency or when you change the reference at the PPC. But we can perform the same tests in a different way and get nice results, okay? So yeah. This is my contact, so my email, my phone, and my colleague. So yeah, again, thank you so much, and I'm here if you have any question, or in the future if you want to contact us. Yeah.
Thank you very much.